So this, in case you see any materials that I have where this talks about section 3.4, the previous version didn't have all the synthetic division stuff in it. So this is the new version 2 section 3.7 about rational functions. So what we need to do is we need to do a little bit of review from way back in chapter 1. And you looked at the toolkit functions, and so we're going to expand on those a little bit. And one of the toolkit functions you saw was the reciprocal function, and that's just 1 over x. And what happens is, if you think about the domain, well, I can't divide by 0, so x can't be equal to 0, and that's so in set notation or interval notation, I mean to be from negative infinity to 0. And 0 to infinity, right? And those be open intervals on each end, because it can't be. And I see this vertical asymptote, and this doesn't have a dotted line, but we know it's there. I can get closer and closer and closer. So as x approaches 0 from the left, it's got a little bit of calculus notation, y approaches negative infinity. And as x approaches 0 from the right, positive side, y approaches positive infinity, and they head in opposite directions. Now, this can also be reflected if it's negative. Sometimes I'll put a number in front. Often it'll be in the numerator. If it's negative, that just reflects everything, and it'll look like this with, the ranges switch. Okay, so that's some things that can happen. So that's the reciprocal function. Now, a variation of this is if I have something like, let's see, if I have 1 over x plus 3, well, that is the reciprocal function that's been shifted left to x equals 3. So that tells me the domain limitation, the vertical asymptote, is now at -3 instead of the origin. And it'll look something like this. It'll just be shifted down. It's got that horizontal asymptote. I'm throwing terms at you that I haven't talked about today, but hopefully we'll do that in a little bit. So that we can, these left-right shifts, these transform functions, they could be shifted up or down, but we don't usually see those or deal with those too much. Yeah, treat those like stretch factors. So here, there's one other toolkit function we need to look at, and that's the reciprocal squared function, and this is in the form 1 over x squared. So it doesn't matter what x is, as long as you square it, it's positive. So that's why the values, so the range of this is always y is greater than 0. Sometimes it includes 0, but that's because it's been shifted up or down. And we'll deal with that later. But to head in the same direction, so as x approaches 0 from the left, y approaches infinity, and as x approaches 0 from the right, the plus sign, y approaches positive infinity. And then it can reflect, right? It could flip upside down, reflect around the x-axis, and that's in which case those would both go to negative infinity. They head in the same direction. And so if you ever see the graph looking like this around what we call a vertical asymptote, you know it's a variation of 1 over x squared. And if they head in opposite directions, you know it's a variation of 1 over x. And that'll come to play here in a minute. Okay, so now let's do let's learn a little bit of terminology here, and maybe you already know this. I know that I can't divide by 0, right? So some number divided by 0, that number isn't in the domain, and that's where the vertical asymptotes happen. So all you got to really worry about is the denominator. So basically you're asking yourself, where does 3 times x plus 1 times x minus 2 equals 0? Well, the 3 doesn't really matter because 3 is 3. If we want to, because it's a constant, we could divide both sides by it. But what we're really interested in is, where does x plus 1 equal 0? Well, that happens at -1. So that's a vertical asymptote. The function's not defined there. And x minus 2 equals 0. When x equals 2, that's the vertical asymptote. So those are the two vertical asymptotes for this rational function. The numerator doesn't matter because 0 divided by a number is just going to be 0. Okay, so actually, while I'm talking about this, what that actually is this is where it's going to cross the x-axis. So we know it crosses the x-axis at -3, 0. And that's not an interval, that's a point. And I knew that because that's when x plus 3 equals 0. Okay, so 0 is on top, x-intercepts on top, vertical asymptotes on the bottom. Now, what's a little trickier about this one to find the vertical asymptotes is nothing's factored. So what I've got to do is I've got to solve it. Now, fortunately, most of these problems that we're going to look at, most of these exercises we're going to look at are factorable. We don't have to use a quadratic equation or quadratic formula. So basically, we're going to take a look at this and ask ourselves, well, how does that factor? Well, x and x, and I think it's going to be 8 and 1, and I know they're going to be one of each, because that's the only way, one of each positive and negative, because that's the only way 8 can be negative. And if I do that, that's -8 plus 1 is -7, so that checks. So where does that equal 0? Well, that equals 0 at x equals 8 and at x equals -1, and that's where the two vertical asymptotes happen. Okay. And aside, and you just think about this for a minute, where does it cross the x-axis? Yeah, I hope you're thinking, well, let's see. I know that x squared minus 4, there's a couple of ways to do this. You could extract the square roots. You could add 4 to both sides, then take the square root, so -2 and +2. So across the x-axis at -2, 0, and at +2, 0. You could also factor this to the difference to two squares, x plus 2 times x minus 2, and that gives you the same answers, okay? So vertical asymptotes in the denominator, 0's on the top, x-intercepts on the top. So what's going to happen sometimes here, though, is you're going to do they're going to look like, for this question, ask where are the vertical asymptotes. So we just start doing the same thing. We have the x plus 3 on top. We have the x, well, it's the x squared plus 4x plus 3 factors to x plus 3 times x plus 1. Now, here's what I want you to notice. If I drop in -3, right? If I find f of -3 or h of -3 in this case, won't that be 0 over 0 times -2, which is 0 over 0, which is weird because I know I can divide by 0. I can't divide by 0, and I know the numerator is 0. So this is weird because usually you have 0 in one place. So this is a situation when you see a 0 over 0, or you don't even have to go that far. If you notice that there's a common factor in the top and the bottom, that's where there's a hole in the graph, not a vertical asymptote. So if I were to graph this, I guess I could throw this in Desmos, but I'll just do it by hand because I didn't get that picture. I know there's a hole at x equals -3. So there's a hole at x equals -3, and there's a VA, there's a vertical asymptote at x equals -1, at x equals -1 because of that piece there. And I also know it crosses the x-axis at -3, 0. So I could just do a little bit of graphing here. Let's see, a vertical asymptote at -1. And then I know there's a 0, it crosses the x-axis at -3. Let's see, 1, 2, 3. And yeah, this one's a little weird. Oh no, it doesn't cross the x-axis at -3 because there's a hole. That helps me. That makes me happier because now I know I don't have to worry about that. So what I see here is I know this graph's going to look something like this, but at -3 there's going to be a hole here. And it looks something like this. So you see how I got the vertical asymptote, and then I just inserted the hole. And I knew more or less it looked like this because this looks like 1 over x. It's just been shifted. It looks like 1 over x that's been shifted left 1. And then, of course, that just takes care of the hole. And we'll talk about how I knew to graph this piece here in a minute. Okay, so pay attention when you do the factoring. If you get a common factor top and bottom, that's not a vertical asymptote, that's a hole. I'm going to ask you, give you a question like this on a quiz, on an exam, and I want you to realize that. Because in calculus, really, this is where calculus starts. We're looking for those places where there's holes in the graph, because there's some special things that we can do with that. And that's calculus, let's not worry about it here. Okay, so now we deal with horizontal. We've been dealing with vertical asymptotes where here, let's get a pen going. Vertical asymptotes happen, where the function's not in the domain. Then they have horizontal asymptotes, and those horizontals, this is the dotted lines that the graph never crosses. Well, horizontal asymptotes are very similar, but we're really concerned about what happens way out at infinity, what happens way out at negative infinity. A lot can happen in between. Unlike a vertical asymptote, the graph can't ever cross it. A horizontal asymptote, the graph could cross it in the short run and then settle down and way out at infinity approach it. Okay, so don't fall into the assumption that a horizontal asymptote will never be crossed. Vertical asymptotes can't be because they aren't in the domain. So let's see. Here's some things you go on to think about with horizontal asymptotes. If you were in a classroom and we had plenty of time to do this, like if you're an Oxbow student watching this, I'm going to have you do some of this as an exploration in class. CCV people don't have that luxury because they don't have the time to expend on it. So I'm going to talk a little bit generically. Way out at infinity, or really big numbers, if I say, let's say x equals 1,000. Let's say x equals 10. That's not very big, but if I look at this n of x number, if I'm finding n of 10, won't that be, let's see, 10 cubed is 1,000 minus 30 over 100 minus 6. Well, that's going to be what? 970 divided by 94. Well, this is pretty darn close to what? To 10? I know maybe 10's a bad number to do that. That's pretty darn close to 10. What happens if I use 100? Well, that'll be 100 cubed, which is, I think, is it 6 zeros? All right, so 10 squared cubed. We've got to go back and think about exponentials here. That's 10 to the 6. So yeah, so one with 6 zeros. 1, 2, 3, 4, 5, 6 minus, let's see, 100 minus 300 divided by 100 minus 6. What I want you to see here is this is going to be a whole lot more than 10 that was happening here. You see, because that's 1,000,000. And 1,000,000 minus 300 divided by 94, that's a huge number. So what happens is as x gets bigger and bigger and bigger, like if I said if I want to find n of a million, say, let's see. I need one more zero and move that comma. Sorry about that. So that would be 10. That would be 10 to the 18th, right? Because you multiply 10 to the 6th raised to the 3rd is 10 to the 18th, and I wrote 16, minus 3 million over, let's see what, 1,000,000 squared is 10 to the 12th minus 6. In the long run, the 3 million and the 6 just don't matter. Just like this, the 30 and the 60, or the 30 and the 6 didn't matter all that much, really. The 300 and the 94, those just aren't going to matter that much. So what we really only have to look at is those leading terms, and because the numerator is growing faster than the denominator. If you think about that, if I have x cubed over x squared, can I cancel out an x squared, and that leaves me an x? So as x gets really big, n of x gets really big. So what that means is this graph doesn't settle down to a horizontal asymptote. And what we call this a top-heavy function. So it's a top-heavy function, because the degree of the numerator is bigger than the degree of the denominator. This is a bigger power than this, so it's going to grow forever or decrease forever if there's some negatives going on, some reflections going on. So this says no, if the degree of the numerator is bigger than the degree of the denominator, there's going to be no horizontal asymptote. Okay, so that's going to be no HA. Now, if they're the same, so if we think about this, remember all that buildup that I just said about how we only have to really care, we only really care about the horizontal, about the leading terms. So in this case, the negative 4x and the 5 don't matter too much, and neither does the 6. We're just going to worry about 3x cubed over negative 2x cubed. Well, aren't those growing at the same rate because the powers are the same? So that tells me the horizontal asymptote is the equation y equals negative 3 over 2. So if it's the same power, same degree, the horizontal asymptote is the coefficients of the leading terms. So if I had 2x to the second minus 4 over 9x to the second minus 2x plus 10, that doesn't matter, that doesn't matter. 2x squared over 9x squared, those are the same degree. That tells me the horizontal asymptote is going to be the equation y equals 2/9. Okay, so same power. Now, if it's a bottom heavy function like this one, let's see. Same power, all right. Here's bottom heavy. Because of thinking about what we did with polynomials, I know in the denominator that's going to be, or in the numerator it'll be 6x, so we don't care about the 4. And the denominator, it's going to be x squared. Well, that's a bottom heavy function. If you think about that, isn't that just 6 over x if you do some canceling? Isn't this just the reciprocal function that's got a little stretch factor going on? So this tells me the horizontal asymptote is going to be the equation y equals 0, the x-axis. And that is because it's bottom heavy. Okay, so bottom heavy, the horizontal asymptote is y equals 0. Same power, you take the coefficients of the leading terms, and if it's top heavy, there's no HA. Actually, there's a slant asymptote. We can talk about how to figure that out here in a minute. If we need to, we'll see. I don't know if we need to go there. Okay, so for this one, they're asking us to find the x and y intercepts. They're also asking us to find the horizontal asymptote and the vertical asymptotes. Well, let's start, since we started with the vertical asymptotes, let's find the vertical asymptotes. So that's where the denominator equals 0. So we want to know, when does x plus 2 equal 0? We want to know when x plus 3 equals 0, because 0 times 0 is 0, so, or 0 times the number is 0. So where x equals negative 2, there's a vertical asymptote. Where x equals negative 3, there's a vertical asymptote. I'm also noticing, and just checking for holes, there's no common factors top and bottom, so I know there's no holes. So let's comment that, no holes. And then for the horizontal asymptotes, we want to think about the degree of the numerator and the denominator. So in this function, if I just start to FOIL it, start to multiply, expand the top and the bottom, I'm going to get 2x squared. And remember, I don't care about the rest of them because those don't have as much effect out at infinity. In the denominator, I'm getting x squared, and of course, same power, so that tells me the horizontal asymptote is y equals 2. They align y equals 2. Notice how I'm writing equations here. I think that's a good form to do. Then we're going to find the x and y intercepts. So the x-intercepts are where the function equals 0. Whoops, be nice how I could spell. Let's see. Here, we'll cheat, and we'll write x int. So that's where the numerator equals 0, right? So where does 2x minus 3 equal 0? Well, it happens at 3 over 2, so at the point 1.5, 3 over 2, 0. There's an x-intercept. And the other one happens where does x minus 1 equal 0? Well, that happens when x equals 1. So there's the x-intercepts. Then the last thing which we haven't really done yet in this video is find the y-intercepts. And y-intercepts are, so x-intercepts are where the function equals 0. You set this equal to 0, ask yourself where is the numerator equal to 0, because remember the denominator is just the vertical asymptotes. As long as those are not 0, it can be any number. Now the y-intercepts, what you're doing, you're finding f of y, or I mean f of 0. So in that case, if I look at the numerator, negative 2 times 0, or 2 times 0 minus 3 is negative 3. 1 minus 0 minus 1 is negative 1. Over, let's see, 2 times 3. Well, I think isn't that 6? Isn't that 3 over 6, which is 1/2? So the y-intercept is the point 0, 1/2. And what we use these things for is just a way to do placeholders to get these to graph. Why don't we try to graph this one? It's a little weird, but I'll show you how it all helps us know what it looks like. So I know I'm going to do an xy axis, xy, and then I know it crosses the x-axis at 1 and it crosses the x-axis at 3/2. I know there's a vertical asymptote at negative 2. I know there's a vertical asymptote at negative 3. I know there's a horizontal asymptote of y equals 2. I know it crosses the y-axis at 1/2. So here's what I know. I know that if a reciprocal function exists like this, or if a function is a form of reciprocal function, the y value is going to go in opposite directions. If it's 1 over x squared, they're going to head in the same direction, either both going up or both going down. Because if we go back and look at this original function, here, I'll try to slide this down a little bit. Neither one of these denominators are being squared, so we know they're both going to act like 1 over x. Okay, so let me slide this back up out of the way so I can see my graph. Whoops. I want to keep my graph down there. I want to move this up here. I think we can delete this. Well, let me delete just that. Yeah. Okay, let's move this up out of the way. Let's get rid of that errant piece. There we go. So I know that out at infinity, this graph is going to approach here. Let me go to a different color ink. I know this graph is going to approach that horizontal asymptote. And I don't know whether it's above it or below it, but I do know that right now it has to cross through the x-axis here. It has to turn around and cross through it again there. It's got to cross through. It's got to cross through the y-intercept. Here, I'm going to flatten those out a little bit. And then it's going to approach, then it can't cross that vertical asymptote, so it's got to head up in this direction. Okay? And then since at x equals negative 2, it acts like 1 over x. So since this is heading up to positive infinity here, this has to head down to negative infinity here. So I know on this side it's going to head down there. And then there's some turning point over here. We could plot some points, but we really don't care particularly. We know it's not going to cross the x-axis because these are the only two zeros. So we know it's got to turn around, and since it can't cross there, it's got to turn around and head back. Head back down. And then since it can't cross the x-axis over here, and it's acting like 1 over x again, I know since this is headed down to negative infinity, it has to head up to positive infinity here. So this graph's going to look like this, and it's got to turn and go out to that horizontal asymptote. And that's a more or less a good representation of what the graph looks like. You can go out and graph that in Desmos and see that I'm not too far off. You're going to see that this is way down a lot further than I drew it. But we really don't care too much. We're trying to figure out, what's a rough sketch of what it looks like. Okay, so let's do a couple more graphing questions. I pulled these out of the textbook. So let's do number 17 first. I think that might be a little easier since it's all factored. So what do I know? I know that when x equals -2, there's a VA. And when x equals 4, there's also a VA. Because I don't see any common factors top and bottom. I also noticed that this is squared, so this is going to either both head to the numerator, head up like that, or it's both going to head down like that. I don't know which. I know this one is either going to go, they're going to go in opposite directions. I don't know whether it's like that or whether it's like this yet. We'll find that out in a minute. Okay, so I know that's true. I know that it crosses the x-axis at 1, 0, at -3, 0, and at 5, 0. Whatever, at -2, -3. Okay, I know. So I guess I'm gonna start doing a little bit of graphing here before I lose all this. Here. If I had more screen real estate, I would not erase it. I would, like you doing this on paper, so. All right. So I know there's a vertical asymptote at -2. I know there's a vertical asymptote at 4. I know it crosses the x-axis at 1, at -3, and at 5. I know the y-intercept, let's see, if y-intercept x is 0, so that's -1 times 3 times -5 over 4, because it's 0 plus 2, then we square it, times -4, so what's that work out to be? 15 over -16, so at just about -1, it crosses the y-axis. Okay, do I have everything I need? Oh, horizontal asymptote. I see this will be x cubed on top. This will be x cubed in the bottom, right? Because that's x squared and another x. So this is the coefficients, or both of those are 1. So the horizontal asymptote will be the line y equals 1. On a test, I would want you to write that out and say y equals 1. There's a HA or something like that, okay? Here, let me clean this up a little bit so I can finish doing my graphing. Alrighty, I think we're ready. I think we know all the zeros, we know the VAs, we know the HAs, we know the intercepts. I think we're ready to graph. Let's see. I know that this graph can't cross this line, it can't cross this line. I know that it has to approach that line, so I'm thinking it's got to cross through here and head out in that direction. Because at x equals 4, it acts like 1 over x. This has to come down for the opposite direction. It's got to cross through the x-axis. It's got to cross through the y-intercept, and then it's got to head down there. And then because at x equals -2, it acts like 1 over x squared. And because this one is heading down to -infinity, this one also has to head down to -infinity from the left. So this graph is going to look something, This graph looks something like this. That horizontal asymptote, cross through that 0, and head like that. So I know that's more or less what this graph looks like. Go graph it on, either look the answer up in the back of the book or graph it on Desmos and you can see. Okay, so that's that one when they give it to us all nice and factored out. Now for the numerator, we got to do some factoring. I see in the denominator, it has a greatest common factor of x squared. So I'm going to factor out an x squared. And so that tells me there's a vertical asymptote at x equals, well, I think there's a vertical asymptote, but x equals 0, because that's the 0 squared, and at x equals 4. And I also know that it's going to act like 1 over x squared at x equals 0. Now for the numerator, I don't see any common factors, greatest common factor, so I'm just going to go ahead and say 3x times x is x squared. I also know that 2 times 2 or 4 times 1, and I know they're going to be 1 of each sign because it's got to be -4. And I see it's got to be 4 in the middle. I'm going to stick the 2, +2 here, the -2 here, because Did I do that right? 6 minus 2 is 4, negative 4. Yeah, so that's right. So I know, I also know, why don't we, okay, yeah, I don't see any common factors, so there's no holes, right? Remember, if this is all factored out and I write it down as factored, I don't see any common factors, so there's no hole. I don't have to worry about that. So there are 2 vertical asymptotes. What else do I want to look at? Oh, I got to find the x-intercepts, don't I? That's why I did all that work. Nope. Let's get it. Let's get an eraser. Don't know if it's going to let me erase that. So let's do a little work here. I know that where does 3x minus 2 equals 0? Well, that's at x equals 2/3. Where does x plus 2 equals 0? That's at x equals -2. The y-intercepts are, let's see, I'm going to go back and look at my original. The y-intercept is, I'm dropping in 0, so that's 0, that's 0. That gives me -4 on top. Oh, actually, yeah, and that's 0 over 0, so -4 over 0. Of course, we knew that was vertical asymptotes. So there's no y-intercepts. Okay, and I see a bottom-heavy function. It's x squared over x cubed, so the HA is y equals 0. I think we're ready to graph. Let's try doing some graphing. Let's see here. I'll have to do some scrolling back and forth. Let's see, here's an x-axis, or y-axis, here's an x-axis. I know it crosses the x-axis at 2/3. Let's see, actually, where's the vertical asymptotes? There's a vertical asymptote at 4. I know there's also one here. I'll just do that in Reading, just so I'll do this one in Reading too. I know it crosses the x-axis at 2/3. It crosses the x-axis at -2. The horizontal asymptote is y equals 0. Did I say that? Yes. What else did I need? There's no vertical asymptote. I think that's all we need. I know it's going to act like 1. Let's do the hard part right here. We know that at x equals 0, this function is going to act like 1 over x squared. I also know it's got to cross both these points. Here's what I think is going to happen. I think this graph looks like this. I think it comes up from that vertical, it's going to make some kind of turning point and head back down there. And I know it's got to act like 1 over x squared, so it's going to go like this. Now I know this graph can't turn around and head back down through the x-axis, so it has to look something like this. I mean, I don't know. It could be some kind of turning point going on there. And then since this acts like 1 over x, that's going to look like this and head like that. And I bet you that's a pretty close approximation of what this graph looks like. And I didn't have to find too many pieces of information to do that. So go get some practice. Go do the ones in the textbook. I recommend that. It'll help your work. It'll help the work on my open math go a lot more quickly. What about this one? Oh, I forgot I had done this. All right, well, let's see. What do we got? I know there's a VA. If you want to stop this video and try this yourself, that would be a good thing to do. X equals, so the VA equals at x equals -1, and I know it acts like 1 over x squared. This one, when x equals -4, it's a 0. When x equals 2, it's a 0. They're both x squared, so the HA will be y equals 1. No holes, right? Yeah. Any horizontal, let's see, any vertical asymptotes or vertical intercept? Let's see. So it'll cross the y-axis at negative 8 over 1, so at negative 8, I think we're good to go. So I get a vertical asymptote at negative 1. It crosses the y, let's see, the x-axis at 1, 2, 3, 4, and at 2. It crosses the y-axis at negative 8, so way down here. Horizontal asymptote, y equals 1. What do you think? Think it looks like, let me get a different color ink. Think it looks like this? It's got to cross that, it's got to cross that, head down to negative. Whoops, I'm kind of running out of space here. And since it acts like 1 over x squared, I know it's going to come up from there, cross that x-intercept, and head out there. I think it looks like that. Folks, I didn't look at this function before I included it. Throw it in a calculator. Do it that way. I know what you do want to pay attention to here is that this won't have an HA, right? Because it's x cubed over x, so it's some kind of quadratic asymptote, and I don't want you to have to go there, okay? So don't worry about this one. So now comes, honestly, find this much more interesting than the graphing. Though it's a necessary evil, you got to be able to graph rational functions to understand what's happening with them. For this one, we're going to write the equation. So some things I'm seeing here with this. I'm seeing a vertical asymptote at 2. Whoops. Here, just a minute, I'm messing up. Here. I see a vertical asymptote at 2, and I see another vertical asymptote at negative 1. I think the horizontal asymptote might be y equals 1, but I'm going to show you another way to do that so you don't have to guess. If they tell you, if you see a dotted line on the graph, then you know that's the horizontal asymptote. Here they didn't tell us that, so I'm not going to make that assumption. I also see that at both of these vertical asymptotes, it's acting like 1 over x, so I know nothing's being squared. I see an x-intercept at negative 4. I see an x-intercept at positive 4. I see a y-intercept at 3, so that's important. So let's write in what we do know, and the part that's easy. So I know I get vertical asymptotes at x equals negative 1, so the factor becomes x plus 1. Remember how you change the sign. And I see another vertical asymptote at x equals 2, so that's x minus 2. I see x-intercepts at negative 4, so I know x plus 4 has to be in the numerator. I know that x minus 3 has to be in the numerator because it changes signs. Now let's see, if I drop in 0 right now, do I get 3? That'll be negative 12 over negative 2. 12 divided by 2 is 6. So there must be some kind of stretch factor here in order to get that negative 3. So let's do this. So there's going to be some a here, some value. So I know it has to cross through 0, 3. So if y equals 3, then x has to equal 0. So 0a times 4 times negative 3. Do you see what I'm doing here? I hope it's just here. I'm just replacing 0 and for x over 1 times negative 2. So that becomes 3 equals a times what? Negative 12 over negative 2, which I hope you realize is 6, right? So 3 equals a times 6. So if I divide both sides by 6, a has to equal 1/2. So that tells me there's a stretch factor of 1/2, which who would have known that? So the best way to write that is put the 1 in the numerator, the 2 in the denominator. And that will give us this graph. Graph it in Desmos and check and see. So you're not too bad. So with this one, I'm seeing vertical asymptotes at, oh man, I'm guessing they usually don't make these things too miserable. So I'm thinking that this is the vertical asymptote, and I'm thinking negative 2 is the vertical asymptote. I'm just guessing. I think that's probably close enough. So I know, and at x equals 3, isn't it acting like 1 over x squared? And actually, at x, for that matter, at x equals -2, it's also acting like 1 over x squared. So I'm going to do this with my denominator. I'm going to say x plus 2 squared times x minus 3 squared. That takes care of the two vertical asymptotes with the 1 over x squared idea. I see it bounces at, there's an x-intercept at 2 and it bounces. I see another x-intercept at 1 and it doesn't bounce. So I'm going to assume that this is going to be x minus 2 squared and x plus 1. And I see a bottom heavy function here, right? That would be third degree over fourth degree. And I could believe that the y equals 0 is the horizontal asymptote, but I haven't used the y equals 1 yet. So if y equals 1, let's see. So there might be something. Well, let's substitute it in and see. If x equals 0, do I get 1? I mean, why do a lot more work? That'll be 4 over. Oh no, that's not going to be anyways close to 1. So we need some stretch factor here. So let's see. So 1 equals 0, I'm substituting in a times 1 times 4 because it's -2 squared over 4 times 9. Well, those 4s are going to cancel out. So I get 1 equals a over 9. So I'm going to multiply both sides by 9. So a should equal 9. Okay. And that'll do it. This one I am seeing, what am I seeing? I don't think there's going to be a horizontal asymptote because that looks like a slant asymptote to me. And we don't have to find it because fortunately, it'll appear for us as we find stretch factors and things. I see a vertical asymptote at x equals 1. And it acts like 1 over x. They're heading opposite directions. I see a 0 at x equals 3. I see a 0 at x equals 2. I see a y-intercept of 2. -2, if I drop in 0, do I get 2? No, so there's some kind of stretch factor going on. So -2 equals a times 3 times -2 all over -1. So that'll be -2 equals 6a, or a times 6. So doesn't a equal -1/3? So -1 over 3, I guess is how I would write that. Okay, so we didn't have to worry about this, that slant asymptote. That just appears there. Now I'm going to add one more slide at the end of this because this example didn't show up, and it'll help you. It'll speed the process for you. This exercise is out of the textbook in section 3.7. It's one of the odd exercises. What's different about this one? Do you see how we have an x-intercept? We have a y-intercept, but the y-intercept's also an x-intercept. Sometimes that gets a little confusing. I do see that, though, they gave me a horizontal asymptote here. So what's kind of cool about it when you see this, that stretch factor is the horizontal asymptote. Because if you think about it, if there's a horizontal asymptote, and let's say the horizontal asymptote is -2, like they told us, we have some things going on here, and we have some things going down on here. But we know, because there's a horizontal asymptote, that these two terms, or these two expressions, have the same degree. So at infinity, it'll be the same power. The horizontal asymptote is right there. So that's what's nice about this. You don't have to worry about finding a stretch factor. Okay, so let's actually finish doing this one now. Let's see, I'm seeing vertical asymptotes at what? If you want, you can stop and try this and come back and watch a video. Or you can go look the answer up in the back if you don't want to watch a video anymore. So x plus 3, and it's not squared because it acts like 1 over x. And then x minus 4, it's not squared because it's acting like 1 over x. I see x-intercept at 3, so x minus 3. I also see an x-intercept at 0, so I could write x plus 0, I could just write x. And then, because it's got a horizontal asymptote of -2, we'll just stick the -2 in there. And that should be the equation. I think I got everything, didn't I? Yeah, the 2x intercepts, there's the y-intercepts also the same. And the 2 VAs, yeah, I think that's it. That easy. That's what's nice about noticing that when they give us a horizontal asymptote, we know it's going to be that automatically. That's stretch factor. Okay, I guess that's it. Probably a way too long a video. Go get some practice.